I like being a wreck, you know, just living life as if, you know,
sleep doesn't matter.
On. Even if nothing's going on, you know, I'm like, oh man, I got a code review to do, and I'm like, blah, 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 scramble, you know, it doesn't even matter.
Yeah, I feel you, because I've been doing some projects. So this has actually been one of the best things over the last few days. I've been doing some projects just for the sake of doing projects.
Yeah.
Because as is all now public, I've handed over atopile, and so I've had a little bit of a graph, which is awesome. And two of the projects I've done, I've just been like publishing little Python things that I've kind of built in one way or another a few times, and I'm like, no, the high quality version of this should exist open source.
Please tell me it's a MicroPython library.
No.
Damn it! Are you a MicroPython hater?
No, actually, I think MicroPython is really cool, and beyond being just cool, a company I worked for in the past shipped a product running MicroPython.
Hell yeah.
And I think even beyond that, I think it has a lot of promise to do for robotics what TensorFlow and PyTorch do for AI.
Yeah, absolutely.
As a configuration layer for underlying kind of like PID blocks or control blocks or something.
Yeah. So MicroPython, for people who, I don't know if we've ever talked about it, but
yeah, no.
I didn't know this until we had like LED matrices at open source, and we had to program them in like a day because they arrived the day before the conference.
Yeah.
And so we just vibe coded in MicroPython.
Have you used Claude Code much?
I use Claude Code all the time.
Dude, it's incredible. So Cursor has got notably worse. I took a gap of coding, and it was just like atrocious. It was like I came back and I was like, wow, I remember Cursor being useful. Like it is actively just getting my way.
I 100% feel the same way, and I so far I think I am a little bit ahead of trends. Like look. Everybody was using Cursor, and maybe I'm not ahead, but Aider is, you know what, I'm not ahead at all. But Aider, which was like one of the first tools, is still the best for like specific tasks.
Okay.
Yeah. Claude Code is best when you don't know what the hell is going on. And you can like, it'll just explore and
it'll just figure it out eventually.
But man, it's expensive.
Is it?
Claude Code.
Uh-oh.
Yeah, but Cursor I have never gotten to work well for me.
Really? Okay, yeah. So Cursor I got to work fantastically for me for a little bit there. Claude Code I picked up, and it feels like what Cursor did in the first place, and I genuinely believe Cursor has got worse. And I think that Claude Code is picked up as better than Cursor probably ever was with the Anthropic models, which were some of the best, but like not a next level amazing anything. It's just really good. It's what I wanted Cursor to continue being. When you were
using Cursor, were you using it end to end? Like, did you ask it to do something and it did it all the way from front to back, or did you also participate a lot in the coding process?
Both, but mostly. So they've got, if anyone's never used it, Cursor is a derivative. It's a code editor that has a code panel on the right side, an extra little panel on the right side where you can ask questions and basically have like an AI chat that can interact with the code. And separately, you can kind of like inline IntelliSense hit tab autocomplete, but much larger AI-based chunks, just like we've had with GitHub Copilot or whatever for years. And I'd use it in both modes. I would use the agent mode on the right-hand side, Command L, chat, discuss how to do something, and then be like, okay, now implement that, as we've discussed. Yeah. But typically pretty small features. Like I need a object that does this. I need a function that does that. I need like that type of thing. People always show they're like, I one-shotted a game that, like, yeah, cool buddy, that's nice.
Yeah,
but to build actually useful things, I think
it's not going to pay the bills.
Yeah, yep.
But the way I felt with like Cursor, I don't know. I feel like Claude Code will do an entire feature and I can work with it to do an entire feature. Versus like Cursor like is more like it'll help you, like, which was good before AI was good. So I don't feel like Cursor was ever good if you knew how to deploy the AI, which like for me, I've always had Aider in the back pocket, and I just flood the context. Like, just flood the context. You'll spend 50 cents, $1, whatever, give it to O3, and it's incredible. Like,
yeah,
I'm a Cursor hater. By the way, also I pay for Cursor and use it, but I don't use any of the AI features.
Just use Zed instead. I've heard great things about it.
I've tried Zed, but until like 2 days ago, Zed didn't let you disable the AI features, but they just announced they let you disable the AI features now. Nice.
The one other thing with that actually is the extension set for VS Code and therefore Cursor, derivatives of it, are incredible. Like the extension ecosystem is, for me, particularly huge because, you mentioned MicroPython before. We're taking a double derivative here. But if you wanted to work in MicroPython, for example, there's almost definitely an extension for that has MicroPython specific commands, tools, upload to board, like execute testing, who knows what it is, but all sorts of useful stuff like that.
We're never going to be able to traverse back up this tree, but on MicroPython, one of the really cool things I like.
We're doing a depth first search. DFS.
So you can write MicroPython and it's Python and there's an interpreter on the microcontroller. It's also very slow, but you can also add a decorator and do MicroPython native, which is going to execute faster, but has some limitations on the language. And then you can do MicroPython Viper, which executes even lower level instructions that are probably going to match C because it's basically going to something like assembly or something like that.
Interesting.
It's very limited. I actually had a lot of trouble getting Viper working because there are so many limitations. You can't even really move variables around. You have to be very explicit about how the data is moving around because a Python integer is actually kind of complex. It can get infinitely big, they scale up forever. Whereas usually when you're doing things fast, you're using a bounded number of some kind. So Viper is kind of hard to use, but I feel like that gives it so much potential because naturally, there's glue code that we don't really care about the speed of, and then there's tough code, like a particle simulation or sending out the data to the LED matrix where you need it to be really, really fast. So I think MicroPython is the right model. I'm just a little upset it's not in JavaScript.
There is one. I have seen embedded JavaScript.
I think it's there, but MicroPython is so solid. You know?
MicroPython's much bigger, and for good reasons too. So actually, as I mentioned, and one of my colleagues who, oh my God, his name's escaping me, but he gave a talk at PyCon Australia on using MicroPython in a product. We both worked at a company. We both worked in the past together. And the reason they shipped this product with MicroPython was because they could prove as a black box, MicroPython did what it needed to do and effectively certify that to a fairly low grade. It's a therapeutic good or in that class of products, but a very low grade one, not, it's not an implant or something, but it was doing image processing. And so you could take the OpenCV MicroPython bindings with the same interface as the desktop OpenCV Python bindings, do all of your development on your desktop to figure out what image processing you needed to do, and then put that same script on your microcontroller and make practical guarantees that it would come out the same.
Hell yeah.
Which is super cool. Yeah. And your development cycle is super tight for that, which I think, actually, if you take that model, right, how that works is your library isn't this Viper type of stuff of trying to compile Python down to C-like performance. Instead, you're just as the classic Python lie, it's all just C or Rust, sometimes C++ under the hood, and you're just binding to things. And so if you use it as kind of like an architectural language and you create an instance of a PID controller and then you basically pipe the data around, for example, you can just let the C underlying deal with that in real time.
Yeah, absolutely.
So
absolutely.
I think that's the way to go.
So much potential. I love it. And then I'm always in my head, I'm always like, how can I make this work with JavaScript? Whenever I see MicroPython's great features, because it's like this.
The JavaScript developers are like that.
We are like that. We always want to convert to JavaScript. But it's like a tension because once you design a whole PCB in TypeScript, you don't want to go into Python. I just wrote the whole, sure. But JavaScript is not, it's not the same as Python. There's a lot of like how we do language embedding. If you want to do C, this was actually very famous. It was all over Twitter. People
blew up the Twitter sphere.
It blew up the Twitter sphere or the X sphere, whatever, what have you. But we have sort of template strings or template literals. And you can put C code in there. So people were making these bindings where you could do PHP code in your JavaScript server, and like you could just execute it as a function. So that works, but the overhead on that is not. It's not like Python where it's kind of like a mutable language. You can override operators and stuff like that. So anyway, TLDR. There's a lot to do there, and that's gonna be a battle. I'm probably gonna end up converting the JavaScript into Python. But you were saying you were creating new Python stuff.
I've been building some projects for nothing but fun, and it's great, my friend. One actually very relevant to this is I made a tool called Pinocchio. Pinocchio, but out. Is how it's spelled for everyone that listening at home. You can find
that's kind of still hard to spell though.
Yeah, I know.
Pinocchio.
It's extremely hard to spell.
I want to throw a K in there. My heart wants to put a K in there, but I feel like there's no K.
Double CH. Yeah, no, crazy. It was a dumb name, but since you infrequently run it, it's okay. What it does is, have you ever heard of the Z3 solver?
Yeah, the Z3 solver is an SAT solver released by Microsoft, I think.
Yes, exactly.
So this is basically an NP-hard kind of problem solver, and it can solve just tons of things, because a lot of things turn into SAT problems.
If you can express it in like kind of advanced mathematical terms of Booleans and sets and formulae, it can frequently solve it for you, and it'll also tell you if your problem is unsolvable, in the sense of like there is no solution, or we couldn't find one, or it might just grind forever. Unclear.
SAT solvers are so interesting because you can describe so many problems in the form of like different constraints or something like that. And so that's super, okay, I'm intrigued.
So very simply, what it does is Pinocchio will solve a pinout for your STM32 microcontrollers. Because you got all these peripherals that can be, each pin has like 6 function. It can go to GPIO, the timer for PWM. It can do a whole bunch of things. But when you're getting high utilization of the pins on your microcontroller, this problem gets really hard of how to get all the juice out of it. It's very annoying. And actually one thing I learned was that, shout out to Narayan, his pinout of the STM used on the Spin, the original one, it was just a small servo drive, was pretty much optimal. You couldn't actually get much more juice out of there. But I was really trying to squeeze out, I wanted to move a few things around, and I wanted to add ideally USB PD from the microcontroller directly, and ideally 1 or 2 other small features. And I was like, sitting here with a highlighter and the printed sheets, which is how you've historically done this, is super annoying. But you can provably now, you give it a YAML file that says, I want 2 SPI buses and I2C, I want 3 GPIOs, blah, blah, blah. You can just lay out what you need and then run it, and almost instantly it'll come up with a table that says, like, this thing goes to here and there, which is great, because then you comment, if it says no solution, you comment one out and it'll tell you there's a solution, this or that. You can derive it all. Very fun.
This reminds me of like my number one like request, kind of like I guess not very solved in EDA tools, is like somebody's like, yeah, so I picked like the pins for my chip, but it's extremely hard to route. Like I cannot figure out, and it's similar. You want to reconfigure the pins you use, or and there's capability constraints and stuff like that to make routing as easy as possible. But in your case, it's just like, how do I assign these pins such that I can get as many of the features as I want? Is that right?
That was the problem I was tackling. So this one won't. You could actually theoretically, because it's just a library as well as the CLI, you could embed Pinocchio as part of tscircuit atopile. I know JITX has this capability to basically let you jump between different pins that could solve for that. But I just enjoyed building it. It's fun to just build some tools for only your own sake. And you can kind of prick around a little with the code quality, just to I rewrote it 4 different ways. And actually, the funny thing is when you prick around enough, you always end up landing on the non-optimal version, because the second idea you had was actually the best one. But by then I was like, no, I'm going back to actually design the thing I want. Anyone who looks at this code, I apologize, it's trash, but it does work. It does consistently work.
That's all that matters. It sounds like it has a clean output. Have you ever thought about SAT solvers for auto layout? So auto layout is one of these, it's like a packing problem. I'm assuming it wouldn't work too well, but I
think it would be insufficiently. I don't think the performance would be good enough.
I see.
And the reason I say that is we actually at Atopile started with Z3 off the shelf to try model our. So for anyone that's used Atopile, I actually can't remember how this works in tscircuit, but you provide physical values as having tolerances and units. So you're nodding. tscircuit does the same.
So yeah, but nowhere near as advanced as Atopile. So you have to provide. You can provide a tolerance, but we won't change part selection based on the tolerance. I think you guys can change part selection.
Yeah, and propagate those tolerances around everywhere, which is pretty cool. So you can propagate all of those, but as soon as you're trying to model these tolerances into things, which I consider a pretty valuable feature, it's actually invalidated a few of the designs that Narayan had in the early days.
Oh, nice.
And he was like, yeah, my little, it was a variable power supply, variable buck power supply. Mm-hmm. He's like, I built it before it works. It's like, yeah, but actually with the tolerance on this resistor, it won't work 10% of the time, right? And the compiler can find that, which is pretty cool.
Yep.
And pretty valuable. But with the trying to solve for these like very set oriented problems where everything's a superset or a subset of ranges of values, continuous sets, Z3 didn't perform very well. It started taking minutes to get to solutions, and there were just more optimal ways to do it.
Yeah.
But it is like broadly a very useful tool. It's just as soon as like the continuous nature of auto layout of like trying to place things in certain ways, and just like the space of the problem to try find a solution is so big.
Yeah, 100%. And then you find out, something wasn't modeled. That's really important. Yeah. It's it's very tricky. Very tricky. I've been working on auto layout for the past week.
Okay.
Again. Well. But there are sort of broadly two groups of auto layout problems I've been working on. A little known, I don't know if anybody has even tried it. I could not find any literature, but a little known schematic auto layout problem, which nobody even thinks of as an auto layout problem. It is a problem, yeah. But you're laying out components in a way that makes sense to a human. Mm-hmm. So it's actually like a more extreme case of like people are going to be extremely anal.
They're very pedantic.
Very pedantic. Yeah. Like if you have just an example, a major no-no, and every electrical engineer would if they saw this, a capacitor should probably be vertical, right? Like
often.
Yes. Basically, I'm struggling to think of a time it wouldn't be.
Yeah. If you're decoupling decoupling DC stuff on like the front, like an analog front end.
Yes, I guess when you get into analog, probably capacitors are allowed to go into
everything gets flipped on its side.
Yeah, exactly. They're like, oh, there's too many, so now we'll do it proper. When it becomes the dominant element or something, capacitive coupling or something.
It's just so vibes based. It's so vibes based.
It is very vibes based.
So and they'll complain about each other's layouts too. Those EEs.
You know what's funny? We just hired someone for tscircuit, and they came to open source. They wanted to come to open source.
Yeah.
And they were talking to people, and I should say, we've sort of like alluded to open source a lot, but one of the most interesting experiences at open source was so many people would come up, stand like 4 feet outside the booth and go, and then they would walk up to us and they would say, what is this monstrosity? You know what I mean? And it was like, putting TypeScript and circuits together was this like this bastard of nature, it's terrible. The two most common words used to describe us were cursed and monstrosity. And you hear it once or twice, you're like, oh, okay, interesting character. But no, it was I should have kept a tally behind the board. But people, I think we won many hearts. So I think people get it after a while.
Once you show them, they're like, "Wow,
yeah,
blessed."
People ask for the reasoning behind tscircuit. They see it as kind of like JavaScript developers getting involved everywhere. But when you think about it, it's like,
well, we're just talking about the firmware.
Exactly. Very controversial in firmware as well. A lot of people also see tscircuit and think it's a firmware project because they can't circuit design as code is also very novel. Right?
Yes, yeah.
But anyway, we hired this guy, and he was at our booth, and he was learning about it. and he was hearing like how controversial things were, and like how different people were, even asking about the differences between atopile and tscircuit in different things, right? And I was
we should say atopile and tscircuit were both at this event. We
were both there,
100 meters from one another.
Yes,
and so I'm sure plenty of people saw both.
yes, absolutely. And but I was like, that is sort of like us versus traditional tools or whatever. That same animosity exists even within the traditional tools.
Oh, yeah.
Like somebody who likes KiCad is going to shit on Altium, and somebody who likes Altium is going to shit on KiCad. You know, it's like going to happen all day. So it's not exactly unique to being TypeScript or. Well, I don't know. I should ask how common those words were at the atopile booth.
Oh, well, I mean, I can't comment for open source because I spent most of my time walking around, but in the mechanical world, it's the same. Like I just, Fusion 360, which people think of in the hobbyist world, and they're corrected, is primarily a hobbyist tool, although there are many companies who could benefit from using it as well as a sketchbook.
Yeah.
Like when I was working in Germany at Lilium, we used NX for the aircraft design, high grade professional tool from Siemens, atrocious to use, takes 15 minutes to start, single threaded bullshit, crashes all the time, painful.
Yeah.
In Fusion, which I was not supposed to have, but I bought anyway on the company card, I whipped it open in a meeting and like live catted in front of everyone to sketch out ideas. Yeah. And I would get to like a viable, like 3D printable, that is, not machinable, CAD model in 15 minutes to demonstrate what I'm talking about.
Yeah.
Live. And we could discuss ideas and tweak it. And so there is a value proposition for a lot of these tools in different ways. And the curse of quote unquote the perhaps professional ones is that they just suck to use. And so there's an application in a lot of ways for a lot of these things.
There becomes a point in every product's life cycle where a checklist becomes more important than usability, right?
Yeah.
Like it's like, do we have that feature or not? Can we say we have that feature? Can we sell based on that feature?
Yeah.
And it doesn't matter if it crashes 50% of the time because somebody needs that feature.
Well, the other 50% of the time it didn't crash, so you got the model.
Yeah, there we go.
Yeah. So it's actually interesting we bring up the usability thing too, because we were discussing firmware before, sort of, with MicroPython. It's sort of firmware. It runs a file system, and so all of a sudden I think it's kind of more software. But Zephyr, commonly, are you familiar with Zephyr?
I heard it before. I don't recognize it right now.
So Zephyr is a real-time operating system. It takes a big nod from Linux, is probably one of the biggest aspects of it. It has device tree overlay type setup and like high-level configuration, but it'll do all the configuration at compile time.
I heard about this because people were recommending it. That's where I heard it. Yeah. Yep. Or like, this thing is great. Yeah.
Apparently it is. I actually have not got deep enough on it to have like a strong personal opinion, but I've heard a lot from people I trust the same thing.
Yeah.
But one of the things is it's notoriously hard to set up in the first place. I've heard that numerously. It's kind of almost a bit of a meme with it. And, really Arduino these days, pretty much all of the ARM-based processors, or pretty much all of the processors these days, is now built atop Zephyr.
Oh, really?
So they replaced the Mbed core, right? Because ARM retired Mbed, and they replaced it with Zephyr. And so now all of that type of stuff is just running atop Zephyr. And really what Arduino is a convenient, as it always has been, is a convenient set of pre-configured examples that gives you a nice environment to get started with.
Wow. Whoa. Okay. Wait, so Zephyr is like a real-time operating system, right?
Yes, but you don't necessarily need to have more than one thread running, right?
Gotcha.
With any RTOS, right? So you can just super loop everything, put everything in the like while true in main, and hey presto, that's your loop function in Arduino. And hey presto, there's actually a lot of firmware that can just be completely super looped.
Wow. This is crazy to me just because, wow. Okay. What kind of stuff? All right. So I'm not a firmware expert at all. What kind of stuff is it bringing to the table, this operating system? When you said Linux, my ears perked up. I was like, I love Linux.
Yeah.
Do I get files? No way.
Yeah, I'm sure. Actually, I don't know about the files, but I'm sure it provides standard file system drivers or a standard interface to have a file system, although you probably don't typically need one.
So it's something I can load in if I want it.
Yeah, the nods from Linux that I know about are the device tree, right?
Okay.
And so your configuration of a microcontroller basically says, there's like literally .dt overlay files, just like in Linux, to configure a specific aspect of your device tree. And you'll say that in order to access some device on the I2C bus, you're saying like via peripheral, blah, 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 I2C bus, talk to this thing. Or via SPI, this and that, like here's how you mux out or talk to this thing. Which is really cool because all of a sudden it standardizes your drivers, just like Linux did, right? Quote unquote kernel drivers.
Yeah.
It's taking that technology aspect from Linux. And then the operating system aspect of it. So are you familiar with real-time operating systems, RTOS?
I've never used one other than maybe I was using it with Arduino, I guess. But yeah, no, I haven't used them.
Okay. So a real-time operating system is the real-time doesn't make any comment on performance or anything like that. It sounds like it might be faster. It's not. All it guarantees are deadlines for specific things happening. And so what it will do, and you can sort of do this with Linux too. You can real-time patch it, and so you get semi-real-time behavior.
Right.
There's this concept of hardness, like hard real-time, where you're like, no, I'm super duper serious that this definitely has to happen exactly 10 microseconds after this thing.
Right. So with normal Linux, your handling of interrupts or something like that, an interrupt could be triggered by anything, but like a button press or something like that. With a real-time operating system, you have a guaranteed okay, after that interrupt happens, it's going to execute. Is that right?
Well, sorry, I've sort of mashed a few things around here. The guarantees that real-timiness makes are how like a deadline for something happening. Right? Like let's look at it that way. That you can guarantee some deadline is going to be met, and how much you trust that guarantee basically is down to the hardness of that.
Okay.
So if you talk about a hard real-time system, you might be talking about some like CNC controls, right? Like it can't just be dropping steps here or there, and like plus or minus a few microseconds like actually matters. You can't just be like willy-nilly being like, oh, I'll send the pulse out to the stepper motor soon. I'm doing something in another thread. It's like, no. It actually needs to happen then.
Yeah.
And so with application processes, it can be harder to make real-time guarantees down to like plausibly nanoseconds, smaller numbers, because all of a sudden you have memory caching and all sorts of other stuff involved.
Right.
And so getting to that level of hardness of real-time can be hard.
So there's a trade-off. Like if you want the fastest speed, like it's my phone and I'm the user isn't going to notice a microsecond, then you would want a normal application processor.
Yes.
But
and a non-real-time operating system.
And a non-real-time operating system. Right?
Yeah, it's typically called jitter. And if you say something should happen once a millisecond on or in a regular operating system, it'll happen once a millisecond plus or minus 10%.
So am I correct in thinking there's like scheduling? Like you can say every 1 millisecond this is going to happen.
Exactly.
Oh, that's very interesting.
So with real-time operating systems, you can have multiple threads, same concept, but you schedule them and they will run, in the allocated slot.
Oh, interesting.
They'll also be preempted by higher priority tasks. So you got task priorities, and you might have some like take the stepper motor controller again, right? You've got a stepper motor pulse output. That actually has to happen on time every time, and it will interrupt other things to make that happen. But processing the command coming down from USB plus or minus a millisecond, like who cares, right?
Gotcha.
So Zephyr offers a real-time operating system to manage all those types of things, like threading, the synchronization between threads, the driver structure, the overlay structure.
It must be pretty small, like if it's going on all these Arduino devices and stuff like that.
Yeah, I mean, it compiles down to tiny.
A bunch of assembly.
Yeah, and plus networking actually is the other aspect that Linux brings to the table typically.
That's so interesting.
You can do well some other way.
I feel like this is a little bit of a tangent, but I feel like it's kind of beautiful how some of the like most complex pieces of software are so few lines of code or like so few things. I was
instructions on the flash.
Yeah. But even higher level, I was looking at the source code for React after it had been minified. And it fits on a browser page, like minified, just all of React.
No way.
In a readable way, yeah.
No.
I mean, the minified code, it has like EB and all this stuff, but it's really, really small. Whenever you install React, you also have to install React DOM or whatever your target is.
Okay.
So React DOM is a lot bigger for actually rendering things to the browser. But the core code of React, the scheduler, the fiber layers, all of these things are really small.
That's
tiny.
super cool. Yeah.
It's crazy.
Yeah.
Our infrastructure, the dominoes are so small.
The dominoes are tiny. The standards are incredible though. That's one of the really cool things about everyone, or like a huge part of the industry rallying around Zephyr, is that the fact that there's a driver for a lot of things and it's pre-configured for a lot of micros, and it's really cool stuff.
I can't wait to try that. I am obsessed with RP 2040s lately, so I'll.
It'll be an easy load.
It's an easy load. Okay.
Yeah.
Right. Easy peasy.
The other one actually, still in the firmware space. If you got one more interesting thing, now this one is not a real-time operating system, but you can plausibly use it to replace one. It's called Embassy RS. So it's a Rust project. That's like, there's actually this quite a good standardization effort in the Rust community for microcontrollers, the embedded Rust project.
Nice.
Which is really cool too. Have you used much Rust?
I've done a little bit of Rust. I've always written algorithms to go to WebAssembly. So that makes me not so good in the microcontroller line. I actually was pushing a little bit for Rust when we were doing hardware projects at Seam, but
it's fairly immature.
It felt immature.
Yeah, a little while ago. I think it's very quickly climbing because there's such a strong Rust community, which is really cool.
It's those damn web devs. There's got to be. Look, I mean, I know we have thoughts about web devs, our listeners and the internet and whatnot, but the web devs they see Rust as passable.
If you couldn't do it in JavaScript, I guess I'll use Rust.
Yeah. It's like the second, and then there's like Go, kind of trying to fight its way up. But that's a whole nother story. You'll never run Go on a microcontroller, I think. It's just not a priority for the Google monolith. Anyway, you were saying this project, Embassy RS.
I'm, coming from the web dev world, you're well and truly familiar with futures, awaitables, coroutines, that type of thing.
Yeah.
So it's this premise of instead of having threads which can interrupt one another, and in a real-time operating system preempt one another specifically, it's a concept of collaborative multitasking. And so in Embassy, you can trade like you would with async await in Python, or Go routines for Go, or futures in JavaScript. And that means that as long as you can ensure that no specific leg of your code is taking too long effectively, it's much harder to make guarantees. You can't necessarily make as stronger guarantees about the minimum amount of jitter that you need.
Yeah.
But the switching time between threads is much, much higher. You're talking like, I think it was tens of nanoseconds for an STM32 to switch tasks in Embassy, and analogously like hundreds of, nanoseconds, microseconds, one of the two. It was orders of magnitude, at least one order of magnitude higher to switch threads for the same microcontroller and the same task.
Wow.
So
why? What's wrong with Embassy?
No. Embassy's the fast one here.
Oh, gotcha.
Because you're switching tasks rather than threads.
Oh, okay.
So you lose some of the guarantees of real timiness that you get with a true RTOS, but the exchange is switching tasks, like yielding to another task, is ballistically fast in comparison. So it's more performant, you get more throughput, you lose some of the guarantees, but you do get some collaborative sense, and simultaneously you don't have to deal with the same inter-thread safety of queues and things. You need like locks for resources because there are multiple tasks, but you don't need to worry necessarily, depending on how you set things up, about atomic writes to memory and things like that.
Yeah. So I guess that makes a lot of sense for maybe like if you're not like, I would imagine as you get bigger, the project gets bigger, those device trees and stuff like that is more useful. Yeah. But if you are just trying to write some blazing fast microcontroller code, seems like a really good fit.
Yeah, totally.
Embassy RS.
Yeah, I've been playing with it for some motor controller firmware lately, and it's cool. It's still like definitely in the young stages, but if you need something quick and it only needs a few tasks, it might be a good way to go.
Are you a Rust fan?
So I'm very much learning Rust, but I do like it. Yeah. I'm about halfway through the book now. I've just been spare time just reading the book.
Yeah.
As interesting social people do.
Yes, yes.
But I do like it, and I see a lot in Rust that is familiar from other languages, and I see a lot of the best bits. The one thing about it is it definitely seems like you need to always use the high level of rigor, which is, the promise.
Yeah.
But sometimes, like Pinocchio, it was just so easy for me to write it in Python because I knew what was going on.
100%. 100%. Yeah. Rust is still definitely... It seems to occupy a space that's like it's harder to use than Python or definitely Python, but also like Go for systems programming, and but lots of really cool stuff if you do need to like balance performance and readability. So
it definitely seems higher quality or more consistently high quality than C++.
Yeah,
and provides a lot of faculty to help you there. And I think that, for true systems programming, it's been C, sometimes C++, and now Rust is allowed in the Linux kernel, right? It's C and Rust. So that's pretty something cool.
Very cool. Very cool. We talked about this forever ago, but this sort of idea of running WASM on microcontrollers is really interesting.
You want more abstraction layers.
I just look. So they say that WebAssembly was a misnomer. People are saying that, and it should have been called General Assembly. That's what people were saying on Hacker News. So these are very official sources. But I get it.
GASM just didn't quite.
GASM. GASM wasn't rolling off the tongue. It is pretty funny because I heard it. I was reading a discussion about it, and people were literally like, "Yeah, GASM is bad," and so they had to come up with an alternative name, like with the general, and that one didn't look good, so
they went with WASM.
Also, WASM does and make it seem very official. If you told me it was General Assembly, I would be like, doesn't really seem.
Sounds like a company
relevant.
from the 1920s.
Exactly. Yeah. General
Electric.
That's right. Yeah. From the golden age.
So the WebAssembly or the General Assembly concept of microcontrollers, it's an interesting one, but isn't it? It's an interesting one because having assembly code implies an instruction set, right? Because assembly code is just aliases for the instructions, if I understand it all correctly, right? And the instruction set is, well, it's kind of a questionable IP thing from ARM in the sense that like there's definitely some uniqueness and intelligence that goes into that instruction set. But really from what I can tell, ARM's primary IP holding is IP blocks to effectively implement that instruction set.
Yeah.
They just don't let anyone compete, really, because they've locked in that. And RISC-V is interesting there, because you could argue that RISC-V is really also a general
it's like, set. Why didn't we just put RISC-V on the web, right? I mean, I don't know.
If it's a set of instructions, really, it's just...
This is coming from somebody who never touches assembly, by the way, so I have no idea. I just love the promise of, like, everything working everywhere. And one of the things I noticed, we were talking about Diode a little bit earlier, is they are working on some WASM stuff. So ostensibly can work on
compile in the browser.
Yeah.
Cool.
That awesome. That is tricky. Although Python might also work in the browser eventually, Yeah. The promise of WASMs.
Yeah, at least works on the back end. That's nice and easy. And you can charge for that. So,
Yeah. Very true. Very true. What are your feelings on Go? Why not get into a little bit of a...
I like Go. I have thought about it. I think the thing is that just everyone I've spoken to who is doing the coolest stuff recently is absolutely using Rust as their primary language.
Yeah.
And therefore, the reason I haven't learned it yet is because I was running atopile, right?
Yeah.
And so that was primarily a Python-oriented project, and very, very focused on its mission. And there was no need for me to learn Rust as part of that project. But now, God, you see just the most cracked engineers around you. Everyone is primary in Rust. And so Go has some nice properties from what I can tell, the Go routines being one of them, the fact that it's sort of co-routinable or collaborative multitasking by default.
Yeah.
Really trivially easily is super nice, and it lends very well to this high performance multitasking as opposed to making guarantees about your safety of multitasking.
Right.
And so like things like web servers, right? And these microservices do super well with it. But, well, Rust also has fairly decent built-in collaborative multitasking. And so you kind of have to work out which, what's worth it.
Yeah. I'm right there with you. Go, great for web servers. Anywhere else? Okay, one thread anything else? I don't know. But one thread we didn't completely close up. We were talking about the analness of schematics and schematic auto layout. PCB auto layout. What's going on there? What do we do? I tried to do a, that's giving me a look like I know too much. I've been trying to crack this egg for the past week. And I thought about it a lot prior to the week, but I had never sat down to do implementation. And my current thinking is that it's not that bad. I don't think it's that bad. PCB auto layout, easy peasy. Yeah, you just pack things together, right? Where does the complexity come in, Matt? What am I missing here?
What's the highest speed signal you've got running around?
All right, everybody starts talking about signals. This is always how we put down the little guy. We talk about signal integrity. So it gets harder when you're doing impedance matching. Is that right?
So. Sort of, yeah. There's the impedance matching. There's like some definitely like a little bit of voodoo art to a lot of these things of like trying to actually get in. I don't know. So like the closest I've ever come to touching this is we were trying to, and I say we lightly because it was mostly Narayan, trying to lay out a the RAM next to an IMX like application processor.
Okay, so we got some serious pins here. Are we talking BGA?
Yeah. Both of them are BGA packages. It's got it's DDR3 RAM, so it's running at like gigahertz kind of scale.
Yeah,
hundreds of megahertz, gigahertz with a wide bus, all synchronized. So your path length has to match, right? Your impedance matching. So you need the path length so the signals actually arrive at the same time as one another, right? You need your impedance matching. So impedance, what this is it's very hard to articulate. Or it's very hard to draw, let alone articulate. But roughly what it is, if you take a 2D slice through your circuit board, there's that shape of your trace and its surrounds are going to have a characteristic, if you go back to your electrical engineering complex maths, like basically a characteristic capacitive inductive property to them, the ratio of these two things, very, very roughly, right? And when you have large changes in your impedance throughout your trace, or when it hits a package, you end up with reflections, basically, from this change, this step change in impedance. And so, among other problems, as I understand it, but I can't get too deep there. But the impedance matching is therefore required for the signal integrity side. The timing is also part of the signal integrity, right? So this is just like quite a hard problem to solve in soft terms that lend well to performant auto routing. It can be solved deterministically if you have some, or it can be helped significantly deterministically.
Can I try to counter?
Please.
And I'm not somebody who's routed a ton of RAM, so just bunk me on that.
Neither have I.
But PCBs, I was looking at the Steam Deck PCB. A lot of these PCBs, even if they have a ton of components, they have a lot of empty space, right?
They do, yeah.
There's a decent amount of empty space. My guess is the empty space is maybe 30%, but probably 50% of the board is just, there's nothing there. And so you can like serpentine and stuff like that, right? You have all this space to kind of work with those traces. My thinking is that it's just difficult to do so, or unreadable to do so as a human. It's kind of it's like more annoying than just trying to find all these kind of like straight segments that work together. So actually the human is sort of imposing this extra constraint that I want it to be super readable and super easy to understand, super easy to do math for.
Yeah. There's also, so if you have, say you're looking at the top of a board and you have two orthogonal traces, so two at 90 degrees to one another. And so one's going left to right, one's going up and down. Well, they're inevitably going to hit if they cross the whole board. But if you have two layers, and very simplified, say you put all the up and down traces on the bottom layer and all the left to right layers on the top, you get an increase in density inherently from that.
Yes.
Because you just from the fact that parallel things never run into one another,
yes,
you get more density out of that design choice. And so it's a common choice for beyond the aesthetics. One, you're solving an NP-hard problem, infinite space.
Yes.
And two, it is a really convenient, it's almost algorithm basically for layout.
We do this in our algorithm. In our auto router, bottom layers have a bias towards vertical.
Yep.
Because if you turn off that bias, like, and it can be like a tiebreaker bias. It doesn't have to be very important, but if you turn off that bias, it just solves less percent of the time. Having this top vertical, like having orthogonal top and bottom, actually makes a difference in solvability.
Yeah.
It's just like, it's not like, it's like better, just straight better.
Yeah.
Maybe different parts of the board you might transition which one is vertical and horizontal, but that's more complicated. But.
So beyond the signal integrity from impedance matching and timing, because they're fairly straightforward. In fact, you can solve them deterministically. Although granted, then you're going to impose additional constraints of these two things now need to be next to one another so the deterministic solver can solve it, right?
Right.
Now, I don't think that's impossible. You go further, you now have high frequency, high current traces for like a motor output, right? Like you're driving a motor at 20 amps and at 20 kilohertz, something like that.
Yeah.
Now, any traces that spend a significant portion of the board parallel to those are going to be coupled to them inductively and capacitively, for that matter. They're going to be coupled to them. And so all of a sudden you're going to be coupling noise onto those traces. And so you kind of have this like almost artsy nous for saying like, I don't want to put shit like too close to those. Now what's too close? Do you put a ground plane underneath them to shield the things on the other side of the PCB? Yeah, like there's lots of stuff.
People also do cutouts, right? Like to stop a signal from traveling.
So the cutouts are less for signal. So there's a creepage and clearance. So creepage is the distance along a surface between two things, and clearance is just the linear, like as the crow flies, distance between them. And creepage and clearance are requirements of higher voltage, right? And so there are just standards that you typically follow, but you can also calculate these arcing distances and what it takes to quench an arc. And AC/DC obviously impacts this pretty substantially as well, the frequency of the AC, all sorts of stuff. But you typically just refer to the spec of creepage and clearance as required by a pollution degree, how much crap and dust and things get stuffed in that board, because it can be vastly more conductive than the fiberglass.
Oh, interesting.
And humidity and a few other factors. And you just punch these numbers into a standard and it says these things have to be 12 millimeters apart because they're 400 volts AC. And you can increase that creepage to the distance, right? Because the creepage distances have to be much longer.
Yeah.
Because there's some like surface effects that improves the conductiveness of an arc and its ability to quench as well, because you start generating plasma off physical things.
We gotta have it. We gotta have an episode that's just a breakdown. We've talked about quenching, creeping.
Yeah, don't be creepy. Anyway, so you put a slot in between these two things. One is a visual guarantee to everyone. Like, don't worry, there can't be any traces between these two things. It makes review easier. But two, because you crack up your creepage distances that way.
Gotcha. Oh, that's very interesting.
Because there's no surface.
How do people simulate this today?
Poorly, from what I can tell. At Lilium, in a 3D space, so a fuse box with lots of bent bus bars, multi-layer stuff. I stuck a small styrofoam ball on the end of a pencil.
No. Oh my gosh.
And like rattled it around in this box until I found holes. Now, this was a preliminary search because I was reviewing someone else's design. So I walked into the design review and went, yep, that's too close. And yep, that's too close. But it's the tools are
so you had a styrofoam ball and then what? It was connected to a wire? Or?
Well, I knew the voltage spec and I knew the pollution degree and etc. So I punched in the numbers, saw the diameter, and it might have been 3D printed. Anyway, whatever. I got a ball, I stuck it on the end of a skewer, and I just rattled it around in the box until I found gaps that the ball couldn't fit through.
Oh, I see. Okay.
Because if the ball can't fit between, there's not enough distance.
Yeah, I'm with you. So there's no way to just like output a spice for your board where like basically like distances between traces and stuff like that are taken into account. Is that right? There's DRC checks. Yes. So you can run a check that, checks for a specific thing,
Yeah.
but that's more of a heuristic. It's not running any kind of simulation, right? So I'm wondering.
It is kind of a simulation. A simulation is just a model of the world.
Sure,
And
sure,
a distance is just a really simple model.
Yeah, that's true. That's true. That's true.
So I would push back on the like, does this need to be more advanced? But the tooling, so there's two things here. There's testability, right? Which is the DRCs. They check things typically in post. There's also layout rules where they will check things kind of as you're dragging around a trace or trying to place components.
Okay.
And those rules are typically like fast enough to run live.
Yeah.
It's really
Are we talking about something more extensive than a keep out rule? We're talking about like, I guess it would be a keep out rule. When you're dragging around a trace, you know it's not allowed to be this close.
Yeah, but how many rules do you need to express everything? This is hard, right? Because if you have, say, a simple board with even only 100 nets on it,
Yeah.
does each net care about every other net? It's 100 by 99. You've got
I
to now,
see.
like
Yeah,
the combinatorics here are really
Pretty
high.
big.
And so that's a lot of rules, one to have, and it's a lot of addition. Like you're dragging this, you want this to be smooth as an engineer,
Yeah.
and all of a sudden it has to check with everything else on the board.
Yeah, this is really tricky because I'm just trying to figure out how to do auto layout. We have an algorithm that can match to templates. And it's so dumb, and I'm almost embarrassed to say like this is probably the future, but honestly, there are a lot of combinations of different PCB designs.
Yeah.
But it is not the most unbounded problem in the world.
Sure, yeah.
There is a lot of footprint reuse and stuff like that. There's footprints that are similar and probably can be substituted to some extent. And so
there's also subsections of the board that are super reusable.
exactly.
You know?
If you can partition, then
Yes.
you can use existing templates. And so my kind of like working theory is that somebody just needs to generate essentially a massive template set and simulate to make sure it auto routes and does all this stuff, right?
Yeah.
But you need a lot of checks to make that happen, or a lot of simulation, stuff like that. And then you've kind of got like a pretty decent auto layout configuration.
Isn't that largely what Quilter's doing?
I have no idea how Quilter works. Do you know how? So for viewers, I almost forgot we were on a podcast for a second. By the way, I'm just like following curiosity.
You're falling asleep, mate. We won't hold you for too much longer.
No, I'm following the curiosity. I mean, it's so interesting. But Quilter is AI PCB layout and routing, I believe.
Yeah, and the amount of AI they use, they've also got like a really good physics simulation built in, so they can do a lot of the stuff that I've mentioned. They can check a lot of the things that I've mentioned fairly live to give feedback to the AI.
Yeah. And they've been advertising reinforcement learning. They're pre-transformer era, so you have to wonder how much they're able to incorporate transformers, or how much they even need to, because transformers are a really great technology, but they certainly are not the only technology to exist. And as transformers get better, GPUs get better, and so everything kind of improves around it. But I haven't been able to use Quilter yet. Have you used them?
I have used them a handful of times, but only when they had their first, like much earlier releases.
I see.
So they were, the boards that we got back did not function.
Oh, I see.
Bluntly. They did not work when I last did it. However, that was now a long time ago. That was 2 years ago.
Yeah.
So is that? Yeah. It was at least a year and a half ago. I'm trying to think of precisely.
This reminds me of Deep PCB. Have you ever heard of this company?
Yeah.
They released a new model recently. I think they released a new model recently.
Apparently, it's pretty decent.
Yeah, I've been meaning to try it out. But
by which we mean like it can sometimes work, which is like impressive for the space.
I'm definitely like, one thing I want to do with autorouting.com is release a leaderboard of the auto routers. And so I need to dig into this. I've just been like delaying it a little bit. But we should definitely produce a data set and do leaderboards for all the auto routers, because it is hard to answer this question. Like right now, what is the state of the art in auto routing?
Yeah.
Nobody knows, and different people are going to claim different things.
Yeah.
And also the time. The time it takes to auto route, I think, I feel comfortable running this benchmark because our auto router isn't really designed for quality. Like there are.
You want to say that on a public podcast?
It's not inherently designed for quality. It's inherently designed for speed.
Naz, blow that out. No. It makes sense. Why? Because if you get something that is like 80 or 90% of the way there, but quick enough that you do it for every board, and then you touch up the bits that you as an EE no matter, you're actually going to use the thing, right? Which, yes, matters.
There's probably two reasons that my theory for building the auto router in a fast way is one, those previews are really important and they provide hinting for auto layout and other parts, so you know how hard a design is approximately by whether or not it auto routes and how much it auto routes by. So that's one. And the second is, I don't think auto routing is a hard visual transformer problem. I think once you actually encode everything in atopile, tscircuit, and you get a VLM, it's going to be a solved problem. There's just no synthetic data set right now.
Plus, if you can, plus if you are willing to write a deterministic router, like we're talking about snaking these traces to increase their lengths, for example, and doing calculations to work out what impedance characteristics something has, or what dimensions it needs to have to meet some impedance characteristics. Look, these are trivial problems, right? They're just not very well integrated with a lot of the tools at the moment. And so if you have deterministic solvers to do things like decoupling caps, like, well, I know I always have to put it right there. I'm not going to run some diffusion model to tell me it needs to be next to the microcontroller. Like, that's just why.
And the other thing is, I think there's a lot of really good reasons to build a fast auto router, but another is, if you can solve a problem, optimizing it is actually way easier. You could have a it's not even a VLM, it's like a diffusion model that is just an optimizer. So it takes worst trace, it takes a section, an image section, and it says that's bad, make it better. And a lot of time, before you order a board, you can get your high quality traces or your higher quality. Ideally, all the DRC checks are passing, and the auto router is also high enough quality to route your board. But it could be harder than that in practice. So just before you go to order, just increase the auto router, or even use another vendor. Like, we integrated with free routing. We run a free routing cluster, and it's slower. That was one of the reasons it wasn't the only reason, but we didn't just go with free routing because free routing is slower.
I do think you've hit on something important here, that morphing a functional design is vastly both easier and in many ways better than trying to start from complete scratch.
Sorry, but the promise of AI generated circuits is somebody can come to you with a shitty prototype, and how much easier is your job as an engineer, where it's can you productize this existing working thing, versus start from scratch, right, where you have to analyze requirements and all of that stuff. It's a little bit weird because we don't want to put out bad circuits in the world, but that's what Lovable and Cursor enabled. They enabled anybody to participate, and therefore anybody to kind of create weird stuff. So really bad stuff sometimes. Stuff where the AI might delete your entire database. I don't know if you saw that recently.
No, I didn't, but I did. I heard whisperings of it. I didn't look into it, but God, it's true.
A lot of people giving their AI too much production access.
It is the thing. I've been using Claude Code, as I mentioned, with atopile recently, and it doesn't one-shot the drivers, but it does save me a shitload of time, a heap of time in writing them myself, which is incredible, because then if all I have to do is review and touch up, easy, and you can also ask it questions like, are you sure the boot select pin should be tied high or low? And
100%.
So, look, it's an exciting future we live in. Thank you very much, Seve.
Thanks, Matt.
Talk soon.
Cool.